And so what did we do last time? What we did is we looked at being able to describe or represent a line in 3D. Unlike a line in 2 dimensions, which you learned in your beginning algebra class, y equals mx plus b for 2D, just a single equation gives you a line. That won't work in 3D. You need 3 equations wrapped up or bundled together as a set in order to describe one line. You do need 2 pieces of information to be able to come up with these parametric equations. You need a point P that actually is contained on the line. Any point will do, as long as they give you a point. And then you also need what's known as a direction vector. A vector, it can even be on the line itself. It's just a vector that's parallel to the line that you're trying to describe. And if you have those 2 pieces of info, that is enough for you to go ahead and give the parametric equations of your line. So, Adriana, I get that. You keep crashing, just keep coming back, okay? As best you can. So let's do planes now. We're going to come back to lines, don't worry. After I do planes, we're going to do lines and planes together. Those are my favorite kind of problems I put on quizzes. They're hard, where you have to know about parametric equations of lines and the equation of a plane in one problem just to complete the one problem. I call these double whammy kind of problems. I love them. So you have to be well versed in my double whammies, and I'm trying to get through as many as I can in today's lecture, and if I don't, you'll wrap up the rest, okay? So what about a plane? A plane isn't a jet plane. When somebody is saying they're describing a plane, it's a surface, and it's a flat surface, like a table or something. And it goes off in infinity directions. So if this is a plane right here, I'm a portion of a plane, flat surface there, like a table, I need 2 pieces of information about that. Let's do a review first, Before we do planes, down here, let's do lines. Okay, so here's a line in 3D. What are the 2 pieces of info that you need to describe this line in 3D? I just got done telling you within the last 5 minutes. Go.
So point on the line.
Good. And? So there's a point on the line. What else?
The direction vector that
parallel to the line, right? It could even live on the line itself. I'm totally okay with that. Heck, we did that in the last problem where we formed a vector like PQ and it lived on the line. So there's a vector V that would be a vector parallel to the line. Here's another vector down here. It's parallel. It's pointing in the opposite of the direction of V, but I don't care which direction it's pointing as long as it's parallel to my line. That's all I care about. Okay? Now let's get to planes. Now when you describe a plane in 3D, good news, you only need 1 equation. You don't need a 3 bundled together in a set like you do when you're trying to describe a line. You only need 1 equation. So don't get confused here, because a lot of students, they fall asleep during this lecture like, and I ask to them to describe a plane in space, and then they give me 3 equations. I'm like, what are you doing? To describe a plane, I only need 1 equation. To describe a line, I need 3 equations. So don't get confused. Make sure you get the distinction. So when you have a plane in space, back to my plane, you need 2 pieces of info, but it's a little bit different from the pieces of info to get the line. Here's the first one that's similar. You need a point on the plane. That's easy. So you'll have some point here, P. Any point on the plane is fine. And the plane goes off in infinity directions. It goes that way, that way, that way, and that way. So I just drew a portion of the plane. Now here's the weird part that you might freak out when I tell you what the other piece of info is. You need a vector, but you need a normal vector. And the word normal in this context means orthogonal or perpendicular. You need a normal vector to the plane. I'm going to draw a picture of a normal vector to this plane in my diagram here. And it doesn't matter if it's pointing up or down as long as it's making, here's a vector right here that's making a 90-degree angle with my plane. That would serve as a normal vector. I'll call it n. What's another vector that would work just as well? Well, I'm going to draw one that's sort of on the underside of the plane, pointing down. That would be just as good. I'll call it n2. Okay? Either one of these vectors, because it's, you know, orthogonal or normal to the plane, would be useful to help me construct that equation for the plane. Now, I'm not going to give you the equation for a plane right off the bat. I'm going to make you think a little bit. I'm actually going to derive it. Because if you ever forget, you can derive it also. So let's look at the derivation and then we'll cut to the actual equation you're going to need. So here's another picture diagram of a plane in 3D. This plane is a little bit at an angle, unlike my plane on the previous page. And we have a point P that lives on the plane. Okay, fine. And then they have a normal vector there. You can see that little square there, which means it's making a 90-degree angle with the plane. And then they have an arbitrary point Q that lies somewhere on the plane. And you don't know his coordinates. We're just going to arbitrarily give him some generic coordinates, X, Y, Z. Now the point P is fixed, and you are given the point P coordinates. Say they're X1, Y1, Z1, okay? And let's say this vector N is given to you, or you have to come up with it. That's sometimes the hard part. With coordinates, or components rather, A, B, C. And so there's the figure on the left. Hopefully you can kind of see what's going on. So this plane consists of all the arbitrary points Q that live on the plane, for which the vector PQ is orthogonal to N. So you need to form the vector PQ, and we'll do that in a second. But let's do a quickie review. When you have two vectors that are orthogonal, what is true about them as far as the dot product of those two guys? Think about what we've learned in the past week and a half.
Equals 0.
Very good. In other words, N dot product with PQ had better equal 0. That has to be true. So we already know the components of N, but we're going to take the dot product of that with the PQ vector, which we're going to form right now on the fly. So remember, terminal minus initial, where Q is just this arbitrary vector having generic coordinates X, Y, and Z. So you're going to go X minus the X coordinate of the P point, and then take the difference of the Y components and the difference of the Z, coordinates, I should say. Z coordinates. And now let's actually do the dot product, because we're getting ready, we're constructing the equation for our plane. Right now, this is how you do it. So you're going to multiply this component with the other component. So A multiplied by the quantity X minus X1, plus, now you're going to multiply the Y components, B times Y minus Y1, oops, that's a parentheses, plus C times Z minus Z1, and this is equal to 0. And folks, we're pretty much done, but you're probably not going to give me the answer like this unless I ask for it, of course. But this is known as the standard equation for a plane in space. And by the way, did I mention that Briggs sucks yet? Not today. Briggs doesn't really give you the standard equation officially, which is unfortunate because most every other calculus book does. And I don't know if you guys can see, I'm kind of in my home office here. Let's see, where's the, So if you look at my books over here, I've got like 27 bazillion jillion calculus books. It's pretty crazy. But all of them have the standard equation for a plane. Okay. So I'm just looking at the chat box. Organic Chem Tutor. Okay, fine. Interesting. Walter Lewin. I don't know about Walter Lewin, but if I were you, there's another gal. I'm blanking on her name. She's supposedly really good with videos on Calc 3. Okay, so here, let's write in this blank here. Are you ready? The plane containing the point x1, y1, z1, that's the point P in the diagram above, and having a vector n which has components A, B, C, normal, so this guy, this N is normal, which is a fancy word for orthogonal. Normal is going to mean actually a lot of different things in this class, which is unfortunate because it gets confusing. Can be represented by A times X minus X1 plus B times the quantity Y minus Y1 plus C times the quantity Z minus Z1 equals 0. That's the standard equation. Now, MyMathLab is probably not going to want you to enter it in like this. It'll probably accept it, but I want you to multiply it all out. So after you multiply everything out, you'll get what's known as the general equation, which is used more often. So there's two versions of the general equation, and they're both fine. My personal favorite is the first one, where you get the variables on the left-hand side, and you move the constant all the way to the right on the right-hand side of the equals. MyMathLab might like it where everything is on the left and 0 is on the right. So they may ask you to rewrite it, or the way their format is. Everything on the left equals 0. Okay? One more way that MyMathLab may ask you, just so you know, after you multiply it all out, a lot of times MyMathLab wants you to solve it for Z. So just isolate Z on one side, get all the rest of the crap on the other. What? Yeah, I'm not making this up. So, you'll get, when you get everything over there on the other side, you'd have like, okay, Z equals some number times X. You'll have like minus AX minus BY plus D all over C, okay? So that's kind of another way MyMathLab may ask you, well, how come there's different ways? It's kind of hard for me to tell you right now because we haven't gotten into the multivariable calculus yet. So I'm just going to ask for now that you accept all the alternate versions of the equation because they're equivalent. Now let's do a classic example. Do you think this is going to be on a quiz or exam? Yes. Put a star by it. If you can't do this problem by the day of the final, I'm not necessarily saying this problem will be on the final, but if you can't, you really don't deserve to pass Calc 3. Quite frankly, that's my opinion. And some other things that you need to know how to do. But this is like one of the most simplistic, classic kind of problems. You should know how to do it. And it's kind of hard. You're not going to like it. Sorry. So let's review. What are the two pieces of info that you need in order to get an equation of a plane? You need a point, and you need a vector that's normal. If you have those two pieces of info, woohoo! You're ready to do the equation for a plane. Well, what if they don't give you those two pieces of info? Like, they don't, would you guys knock it off? Then you have to work it and use all of the tools in your toolkit to help you get what those two pieces of info are. And if you can't, then prepare to die. Okay? And that's the hard part of all the examples I have today, is being able to figure how to get those two pieces of info given all the tools in your toolkit. So listen up. I'm going to draw a picture here and then we'll work it. So let's say you have a plane here and they're giving you 3 points, not just one. So thanks, guys. You gave me 3. I just needed 1 point. But you gave me 3. And you can label them whatever you want. How about just P, Q, R? So I don't know. Here's P, here's Q, here's R. I got 3 points that live on the plane. Thanks. Now what? Well, I wish I had a vector that were normal, aka orthogonal to the plane, because then I'd be good to go. We have to go get it. So let me walk you through the strategy, the game plan, and then we'll do the game plan. So step 1 is going to be form a couple of vectors, and it's up to you. I'm going to do PQ and PR, but you could, if you wanted to, do PQ and QR. I don't care. It doesn't matter to me. But out of those 3 points, construct 2 vectors. So I'm just going to do PQ and PR, and hold on a second. Let me put the Q over here. How about this guy be the, it doesn't really matter, but it'll be easier for you to understand the right-hand rule. Let me make the Q over here and the R over there. Still got to go get PQ and PR. So that's going to be step 1. Then what? Then you're going to do the cross product of PQ cross PR. Well, how come? Why the heck do we need a cross product? Because we need a vector that's orthogonal to the plane. Right now we have two vectors that live in the plane, which is nice, thanks a lot. But remember, the other piece of info is I need a vector that's normal to the plane. And I claim that this cross product is going to give me a vector that is normal, aka orthogonal, to the plane. And using the right-hand rule, putting my fingers first through Q and then curving them around through the R and then closing my fist down and leaving my thumb pointing, I claim with my right hand here, my thumb is going to be pointing up. I know that's a pretty sad diagram of a hand. But I claim, whoops, that a vector that's going to be pointing up that is orthogonal to the plane, this PQ cross PR, is going to give us what we need. And then we'll be able to complete the problem because we have our two pieces of info and then we win the game. That's how we roll. So I'm going to do this in order. So first, form PQ and PR. And remember, terminal minus initial, okay? So the PQ vector, given the points PQ and R the way I've denoted them, and you can label them how you want, because again, it doesn't matter. You could have formed the vector QP instead, and still, as long as you take a cross product, you're good. 4 minus 1, 1 minus 1. And using the arithmetic here, I get this vector, negative 2, 3, 0, in component form. The PR vector, I'm going to do terminal minus initial, negative 2 minus 2, then 1 minus 1, then 4 minus 1 for the last component. And that gives me in component form, negative 4, 0, 3. Fantastic. Now I'm going to get the cross product. So PQ cross PR is next. And we already went over how to get cross product, right? That was this week's material. So you know, if you use the 3 by 3 determinant method, so I'm going to make a 3 by 3 determinant here. I hat, J hat, K hat is in the top row. By the way, if you neglect putting that top row because you're in a hurry, I'm going to dock you a point. I want to see this in excellence on your handwritten work. Then I'm going to put the PQ vectors components in row 2 and the PR components in the last row. And then you know the drill. You're going to have a 2 by 2 times I hat minus a 2 by 2 determinant times J hat plus 2 by 2 determinant times K hat. And blocking out the row and column that I hat lives in gives you the elements of the 2 by 2 determinant for the I hat. Blocking out the row and column that J hat lives in, copying those down. This is a key student error, is copying them down wrong. A lot of times students miss a negative when they're copying stuff down. Then all hell breaks loose and the whole problem goes down the toilet. And it's sad. And I've done the same type of mistake. You know, your teacher's not exempt from silly mistakes. It happens to all of us. So just be careful. So then doing the 2 by 2 determinant, you multiply the elements along the major diagonal minus the product along the minor diagonal. Okay, here you're going to get negative 6 minus 0. And this is a minus here in front. Oops, don't forget. So that's times J hat. Plus, and then here we're going to get 0 minus a minus 12, K hat. And then this guy is going to have components 9, positive 6, 12. Okay, cool. There is a vector that is normal to our lovely plane. Turn the page because I run out of room. So now what? Well, the good news is I have all the info I need. I have a point on the plane. In fact, I have 3 of them. And I have a vector normal to the plane. So to do the standard equation for the plane, which we're going to start with here, and Briggs has it doing a different way, and I really appreciate it if your intermediate step, you do it my way on your homework. Some people just never listen, though. I tell them, please do it this way, and they just do it the Briggs way. So you're going to put your A, B, and C. For us, the A, B, and C are 9, 6, and 12, respectively. And then the point that we're going to use, the X1, Y1, Z1, oh, shoot, we have 3 points. Which one should we use, or does it even matter?
P.
Okay, this is where I'm going to start calling on people. All right.
Is it point P?
Okay, Anthony, that's fine, but what if I use point Q? Would that be bad?
Does it? I'm
Oh,
getting,
no, it doesn't matter.
Okay, Danielle, I'm talking to you. What point should I use P, Q, or R, or does it matter?
I don't matter.
Say that again.
I don't think it matters.
He doesn't think it matters. Does anybody want to challenge her on that, or do you agree with Danielle on that? Talking to the whole class now.
I agree with Danielle on that. I
Agree
don't
with
think it
Danielle
matters.
on that? Nicholas thinks she's right. Adriana agrees. Elvis agrees. You all are correct. Thanks, Danielle. That is true. It doesn't matter. So pick whichever one of those points is your favorite guy. I don't care. Pick a point.
Is that because the points are all on the plane,
Yeah,
so it doesn't matter?
just pick one. Doesn't matter. And then the final answer after you multiply it out, believe it or not, will be the same. You end up at the same spot after you multiply it out. Initially, it might look a little different because your standard form. But so here's the deal. I got my 9, and I'm just going to use point P if you don't mind. Okay, so I'll use the point P in my example, but you could use whichever point you like. So 9 times the quantity x minus 2 plus the 6 times the quantity y minus 1 plus the 12 times the quantity z minus 1 equal to 0. It has to be an equation, not an expression. If I don't see the equals 0 part, if I don't see an equation, I'm going to dock you lots of points. That's like yucky. Now I'm going to multiply it out. This is just the algebra part. So after distributing and cleaning it up means I like to get the
Point P, the -2 was point P -2, or am I mistaken?
okay, point P had coordinates 2, 1, 1. Yes?
Oh, okay. So it's
So in the
+2 for
standard
the x.
equation here, you got to keep your eyeballs on the ball there. If you'll notice, if you're just substituting in all the right slots, George, that you have to have the minus sign before the coordinates. So I think
Oh,
I'm
good.
okay. I'm doing it in alignment with the theorem. You with me?
Yeah, it's right.
Hello? So now if I collect the variables next to each other, and then if I look at the constants here, what the heck does that add up to? Oh my goodness. -36. How about if I add 36 to both sides? Because my favorite look is that, where the constant is on the right-hand side. Again, my math lab may ask you for a different format, so follow directions if you want all your points. Part of this class is following directions. Now, I would dock you 1 point for this, even though this answer is perfectly good. Why would I dock you just 1 point? Because I claim it's not totally simplified. I claim you can reduce this equation a little bit. What do you mean? Well, look at all of the numbers that occur in this equation. You can only do this if it really does reduce. Is there a common factor, a greatest common factor of 9, 6, 12, and 36 that you can think of?
3.
Yeah, so if you divide both sides of the equation by 3, it just looks a little prettier, okay? I mean, it doesn't do much. It's still equivalent. But this is very traditional to try and reduce your equation if you can. Now, that's not always possible, but in this case it was, so we go do it. Okay, I'm done with the entire problem. Yes, it took a while. If you're the kind of person and you get impatient if you don't finish a problem within a minute and a half, this class might be trying a little bit of your patience, so be patient. Any questions on this problem?
Question actually, was every point on the plane orthogonal to it, or just Q?
No,
Yeah,
when you
P.
talk about orthogonal, only vectors are orthogonal to each other, not points.
Never mind.
I'm just trying to clean up your language here. So this vector, this normal vector, is indeed orthogonal to the 2 original vectors that created him, the PQ and the PR, by definition, from what we learned about cross product the other day. Does that help?
Yeah.
Okay, I'm going to move on. I got lots of examples to do. This is a double whammy kind of problem. Why do I call it a double whammy? Because you need knowledge of lines in space and knowledge of planes in space all together just to be able to understand this problem. And if you don't, prepare to die. And yes, it's going to be in the homeworks. Yes, it's going to be on the quiz. Yes, it's going to be on the midterm. And yes, it's going to be on the final. Like, yes, 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 yes. That's the answer. Yes. So let's try to visualize it, and then we'll get to it, okay? So what are we doing here? What am I doing here? So we're trying to find the equation for a plane. That means one equation that passes through this point. Oh, good. They gave me a point that lives on my plane. Thanks, guys. That was really nice because I do need a point on the plane. And I remember the other piece of info I need is a normal vector to the plane, but it doesn't look like they're giving me that in the next sentence or the rest of the sentence. It has a normal line, but not a normal vector. So if I draw a picture of what's going on, and you don't have to draw pictures, but I highly recommend it because it can help you. So there's a line that punctures or pierces the plane, and this line, I'll just call it line L, it's normal to the plane, and that means it's orthogonal. So that means it's making a 90-degree angle as it intersects the plane. Cool! So it is making a 90-degree angle. And then they gave me the parametric equations for that line. Nice. But I still don't have that normal vector I need. So the good news is this is a super easy problem, no cross product needed. If you start doing cross product on a problem that needs no cross product, I don't even grade the rest of that problem. You immediately get 0 points. It means you didn't understand the problem. So be careful. So do you guys remember that in order to come up with the parametric equations for a line, you needed a point that lived on the line, and you needed a direction vector for the line. And the direction vector's components actually end up being the coefficients of the plane, of the line, sorry. So the direction vector you can easily obtain by cherry picking the coefficients of the parameter t, found by cherry picking the coefficients of the parameter t. So what am I saying? The direction vector for this line is this vector, -5, 3, -1. And you're probably thinking, yeah, so what? Well, folks, that the vector that lives on the line right here, this vector v, right here, can you see even just visually that this vector v is in fact normal to our plane? Please say yes.
Yes.
So the vector v is going to be the same as our vector n. So claim we can use v for our normal vector to the plane n. They're one and the same, people. We'll call, we'll just rename it. It's the same guy. We'll just use him because he's a vector that's already orthogonal, normal to the plane. Fantastic. So now do the standard equation for the plane. So you're going to have the first component of your normal vector. So this is the same as n, essentially. And then you're going to go x minus the x coordinate of your point, plus the second component of your normal vector, y minus a -1, plus the last component of your normal vector, -1, times the quantity z minus 7, and that whole mess is equal to 0. And then clean it up by distributing these coefficients there. So you're going to have -5x plus 20 plus 3y, and this is really a plus because y minus -1 is y plus 1. So that's going to be after distributing 3y plus 3, and then you're going to have plus -z plus 7 equals 0, and then get all the variables on one side and then add up all the constant terms, and I get 30, and then move them to the other side by subtracting 30, and you're done. Now I'm going to tell you another secret of making things pretty. This equation is already reduced. In other words, there's no common factor to all the coefficients and a constant that would reduce this to lower terms. However, we're still going to reduce it. Really? Listen up, because I know some of you are going to go, oh, that's really just like picking hairs. And I'm going to say yes, but we can. Notice how this equation has a lot of negatives in it. Like there's a couple of the coefficients are negative and the constant is negative as well. Well, we don't like, you know, negative attitudes. So we're gonna multiply both sides of this equation by -1. That's legal. And we'll obtain an equivalent equation, but it's an equation that doesn't have as many negatives in it. So it looks a little more pretty, that's all, okay? Now, I'm not saying you're gonna lose any points off of MyMathLab if you have a very negative looking equation. I think you'll be fine, but I'm just giving you tradition. Okay, there you have it, and I'm done with that problem. Questions?
We can assume that the coefficients of t are basically the components of the direction vector.
Always, and it's not just that you assume it, it's by definition. Let's go back to the parametric equations for a line we did on Wednesday, so I can remind you that my cherry picking is totally legal. So remember this, the parametric equations for a line in space? Can you see my
Yeah.
screen okay?
Mm-hmm.
You recall that the direction vector, which has components A, B, C, the ABC ends up being the coefficients of the parameter t in those parametric equations.
I see. Oh.
Yeah?
Mm-hmm.
So when you cherry pick them, you're just using the definition because you know these equations through and through. And then the x1, y1, z1 are simply the coordinates of a point that lives on that line. Remember?
Okay.
Does that help?
Yes.
So what I mean by double whammy, let's go back to recapping this problem, is if you don't understand both parametric equations for a line and the equation for a plane in space, then you are not going to be very good at these double whammy problems. You got to know it all. And I'm really in favor of these double whammy problems because I like to pick a problem that sort of tests everything in one shot. It's really great for us teachers. Okay, now let's look at the angle between two planes. This is not in Briggs, but it is in every other calculus book. So because I have access to other calculus books in your MyMathLab, there will be homeworks on this and you are responsible for this concept. But it's not officially in the Briggs text, which is unfortunate. Briggs is kind of lame when it comes to Calc 3. I was talking to the department chair of math over at City College, and we were just talking about good calculus texts and bad ones, and he said, yeah, well, we use Briggs for Calc 1 and Calc 2, even though it's also not, he agrees, it's not the best text out there. We're not big fans. But he goes, it's so bad for Calc 3 that we actually don't use it for our Calc 3 class at City College. And I went, really? And I just thought, we don't have that option here at Southwestern. Don't ask me why. Okay, before I do this, let's do a quick review. Do you guys remember how to find the angle between two vectors in either 2D or 3D? How do you get that angle?
Is it where like you take the dot product equation and you solve for the cosine?
Yeah, so you know that cos theta is equal to the dot product of those two vectors divided by the product of their magnitudes, and then you simply arc cos or take cos inverse of both sides of the equation there, and voila, you have the angle between your vectors. Okay, hopefully you remember that because that's going to keep coming up. Don't lose sight of that formula. Well, how does that help us get the theta, the angle between two planes in space? So here's a picture for you. I hope you can see that you've got the light blue here is a plane, and then this pink one down here is a plane, and this angle here is the angle between them. How do you get that angle? Well, here's what they basically do. They say, screw trying to find the angle between the planes. Let's just find the normal vector to each of those planes. So here's N1, that's a normal vector if you extend it to the pink plane. And N2 is a normal vector to the light blue plane. And what you do is, or excuse me, maybe I said the opposite. I think N2 is actually the pink guy's the normal vector. And then if you find the angle between those two normal vectors, it's going to give you the same answer as the angle down here between the two planes, with a little twist to it. So what I want you to notice in this diagram, after getting rid of some of this, is remember that the picture here is only showing you a portion of these two planes. So if I extend the pink plane out a little bit more, because it really keeps going in all directions forever and ever, and if I extend the blue plane a little bit more, you know, he keeps kind of going down forever. Do you notice that there's another angle that we could be talking about that we're not addressing? The obtuse angle on this side. So what are they interested in when they're asking for the angle between two planes? Not the obtuse. They want to keep it to the acute angle between the two planes. So how do you guarantee that you're going to get the acute angle and not the obtuse version? What you're going to do is you're going to use this formula here, but instead, of course, of just any vector u and v, we'll use those normal vectors. So let me just show you a little extra that you're going to need to do to ensure the acute. Because you want acute, this means the cos theta needs to be positive, because you want to stay in quadrant 1 and not be over there in quadrant 2. So to guarantee that your cosine is positive, you put absolute value bars around the dot product. And that's how you ensure that you get the acute angle between the two planes and not the obtuse one. Okay? We'll do an example right now, but first let's fill in these blanks. So what if you have two planes that are perpendicular to each other, which could happen. You know, like in my office here, my floor is perpendicular to this wall. You can think of the floor as a plane and my wall as another plane. It looks like they're making a 90-degree angle over there. So they're perpendicular if their normal vectors dot product is equal to what?
It can be a lot harsher than they're meant as.
0.
Thank you. They're parallel if what? N1 is equal to a scalar multiple of the other. And it doesn't matter what order. You could also go, well, N2 could be a scalar multiple of the other guy. Yeah, either or would mean they are parallel. Or if you really want to impress me, what's another way to prove that two vectors are parallel? I'll give you a hint. It involves cross product.
Cross product equals a zero vector?
Yes, very good. That's another way to show that the planes are parallel. So this also works. Pick your poison. Okay, so let's take a look at an example of finding the angle between two planes, okay? So here they're giving you an equation of a plane right here, x minus 2y plus z equals 0, and another equation for a different plane, 2x plus 3y minus 2z equals 0. What's the angle between those two guys? Well, the first thing that you need to do is you need to go get a normal vector for each of them. So we need to figure out n1 and n2. How do we do that? You're going to do some more cherry picking. Let's talk about the cherry picking here. If you look at the equation for the plane theorem, and this means you know stuff, people. Like this is how I'm going to find out if you're really paying attention to my lecture or you're passing out. Notice that after you multiply everything out and you get, you know, one of these babies, preferably, if you look at the coefficients for the variables x, y, and z, when all the variables are on one side of the equation, please. Don't use it for this over here. That'll give you a little bit wrong. But either of these first two, the a, b, and c are the components for your normal vector. So you just cherry pick off the coefficients of your variable if you have it in general form, and voila, you have the normal vector without having to do any more work. So knowing what I just said, if you were paying attention, what are the component forms for the two normal vectors for these two planes? Go.
Got 1, -2, 1
Yep,
for n1.
yep. And somebody other than George. I'll call on somebody now.
My
Okay.
turn, my turn. Never
2, 3, -2.
Okay, good. 2, 3, -2. Very good, because those are the coefficients for the other plane. Now you're ready. You have what you need. So your cosine theta, when you're finding the angle between two planes, you have to take the absolute value of the dot product to guarantee that you get the, so in this blank here, you're going to put absolute value of dot product. That's how you guarantee you're going to get the acute angle. Now don't do this if I ask you for the angle between two vectors. When I ask you for the angle between two vectors, you don't take no stinking absolute value, okay? That's only when I ask you for the angle between two planes. Please make this distinction for yourself, because I'll get a student get something wrong on a test, and they go, oh, you told me to take absolute value. And I'm going to go, sorry, you got confused. You are not listening. I said, do only the absolute value if it's the angle between planes. So, you know, I get people that, you know, they listen, but only halfway, and then it hurts. So you're going to take the absolute value of, and I'll do the dot product in slow motion here. So if you're in degrees mode on your graphing calculator, this should work. I get roughly 53.55 degrees, and that is an acute angle. So there you go there. And now I'm going to do a really hard problem. Yeah, because I can. So this next question is a continuation. This is example 5, part B. So we're still dealing with the two planes that we started off considering up here. So that's still going. We got the angle between the two planes, fine. And now they want the parametric equations for the line of intersection. So let me draw you a little diagram to help you visualize what they're asking for, because this is a classic problem. Hint, hint, I'm probably going to put it on a quiz and an exam, like for reals. So I hope you can tell where these two planes intersect is a line. And PDF annotate when I kind of go over something. And because those planes go off in infinity directions, of course that line goes off infinity directions also. Another way of visualizing this is when you look at a book and you kind of crack open a book, you can think of the pages representing a plane, and then the binding representing a plane, and then the line of intersection is where they're bound. Okay, the spine, if you will, of the book. That could represent your line of intersection of the two planes. Now this is a hard problem, and there's a couple ways to do this problem. If you've taken a linear algebra class already, they ask you to do this kind of problem in a different way, because they give you a system of equations like this. It's two equations and three unknowns, which could either have one of two, well, one of the answers, of course, is x and y and z all equal 0. But really, there's infinity solutions to this system of equations. And the infinity solutions are all the points that live on this line of intersection. Okay? So, when you're trying to find parametric equations for a line, keep in mind we need a point and a direction vector. And we don't have any of that yet. We're like, eh! Now, you could go, oh, as long as I get a point on one plane, that's a point on the line. No, because if I got a point way over here on that plane, like right here, I'll call it point P, that doesn't even look like that point is even close to being on my line. So don't just pick any point because you feel like, oh, that feels good. No, it needs to be a point on the line of intersection, which means the point has to satisfy both of those equations, not just one of those equations. So here's a quick and dirty technique for you to help you get it. And by the way, if you've already taken linear, this is known as a homogeneous system of equations because the constant on both sides of the equal sign is 0, and that's what's known as a homogeneous system. And you'll learn in linear, there's always a trivial solution to a homogeneous system. And the trivial solution is always 0, 0, 0. The point 0, 0, 0 will always work. So let me just prove it to you though. So a quick way to tell that 0, 0, 0 is actually going to be a point that lives on both planes, hence the line, is zero out one of the coordinates. Like, hey, for both of these equations, let z equal 0. Just force it. Then what? Well, then you have a system of equations that's only 2 equations and 2 unknowns. And you learned how to solve this in your baby algebra class, right? So from your algebra class, you can use either substitution or elimination. I'm not going to do this for you because this is going to take some time, and I assume everybody in the room knows how to solve a system of 2 equations and 2 unknowns. The answer you get is x equals 0 and y equals 0 also. So what does that mean? The point 0, 0, 0 is a solution to the system, which further means that it's on the line of intersection. And that's the point that we're going to do business with. Cool. Now what? Well, we still don't have a direction vector. That sucks. So there is a linear algebra way to do the getting of the direction vector, which I'm not going to do. But if you want to see me during office hours, I'll go do for you, but I don't want to here because this is not a linear algebra class. It's a Calc 3 class, although they do have a lot of overlap, I must say. In fact, I have a student right now who's in my programming class, and he had me for Calc 2, and he was like the other day, hey, I noticed you've got room in your Calc 3, because it says on WebAdvisor I have 6 seats available. And can you give me an ad code for your Calc 3? And he's taking like linear and my computer programming and physics. And I went, you've already missed 3 quizzes and 5 lectures. So no, I'm not going to let you in. It'd be wrong for me to do that. You're going to die. And he goes, well, you know, in this linear, it's very conceptual. And I go, yes, it is. And he goes, yeah, and they're doing vectors for the first week. And I went, should have taken Calc 3 first. Anyway, I digress. So how do you get this direction vector? So back to my picture up here. I claim that for this picture, if you've got a normal vector to the first plane and you've got a normal vector to the second plane, the cross product, and you can use the right-hand rule and check me on this, will be equal to the direction vector for our line of intersection. Believe it or not. And or if you want to do it backwards, like N2 cross N1, just as good. I don't care what order, because all we need is a vector that's parallel to our line. So using the right-hand rule where my fingers curve through N2 and then N1, my thumb's going to end up pointing after I close down my fist here. My thumb will be pointing, this is for N2 cross N1, in this direction that's coming out of the paper. And if I did N1 cross N2, my thumb would be pointing in the opposite direction going into the paper. Doesn't matter which one though for this particular problem. So my claim is N1 cross N2 will serve as a direction vector for our line. Well, I guess we're doing a cross product again, you betcha. So I'm going to cherry pick, well, we already did cherry pick the N1 and N2 up here from part A. So I'm just going to use those to do my cross product. So here we go. N1 cross N2, use my 3 by 3 determinant, set it up. I hat, J hat, K hat goes across the top. 1, -2, 1, 2, 3, -2. I'm just going to say etc. I'll let you figure it out because you've seen cross product lots of times now, hopefully. The cross product is 1, 4, 7. And so now your parametric equations for your line, using the point 0, 0, 0 as the point, so we don't even need to put the zeros in there. These are going to be the coefficients for t. And remember, parametric equations for a line are not unique. So like if you had -1, -4, -7, that would be fine because that's also a vector that's parallel to your line. So your answer might be x equals -t, y equals -4t, and z equals -7t. That would be fine. Or any scalar multiple of 1, 4, 7. Okay? Now, this is a harder problem that's the same problem that we just did, but it's harder. Why? Because it's not a homogeneous system now. And you're not guaranteed that the 0, 0, 0 is going to be on your line. So I'm not going to do this whole problem. I'm going to start it off and let you finish it. And yes, there's going to be a problem like this in my math lab. Don't even ask me that, okay? It's like yes. Yes, yes, and yes. So how do you get a point on the line of intersection? So we're going to use a similar strategy like we did before. Force one of the variables to be 0. And it doesn't even have to be z. Like on that previous problem up here, I forced the z to be 0. And then I had x and y in my system of 2 equations and 2 unknowns. I could just as easily have made a command decision and said, well, instead of setting z equal to 0, I hate x's. And I'm going to kill off the x's and make them zeroed out. And then I'd have a 2 equation, 2 unknown system that would have only y's and z's in it. That's also legal. Whichever seems to work best or going to be easier for you to work with. So in this problem, let's see, what did I do in my notes? Did I do, yeah, I said, okay, let z equal 0. And then solve this system of equations. Okay, and I'll let you do it. And it turns out the answer to this system is x equals 3, y equals 1. So what does this mean? It means the point with these coordinates, 3, 1, 0, remember you forced the z to equal 0, lives on the line of intersection. Okay, then what? Well, then you got to get that direction vector. So then what? How do you get the direction vector? Again, you're going to take the cross product of the normal vectors of the 2 planes. And I'm not going to do this. You'll do it. You cherry pick off the components of your normal vectors, take the cross product. Your final answer is going to look like this. X, Y, Z equals, so you're going to have your points, 3, 1, and I'm going to put the 0, and you'll end up with -3t, 3t, -3t. Or your coefficients of your t parameter had better be a multiple of mine, and then it'd also be fine. Okay, so I'll let you finish that one out, knowing now what the answer is. So go do that, and now let's go to a new topic. Yep. How do you sketch planes in space? Well, I know it's hard for some of us to visualize and even draw things in 3D. I'm not that great. But there are a few things I'm going to ask you to sketch in 3D. Okay, so in 3D, you are expected to sketch a plane in space. I'm not going to usually ask you to sketch a line in space. You know, that would be probably best given to, 3D coordinates graphing, like I was showing here at the beginning of the class. I was graphing a line here in space. And, you know, you can use these 3D graphers to do that. But planes in space, you should be able to graph nicely. For example, in mine, this cool system up here, this is called NewCalc. What I like to do is, like, if I wanted to graph a plane, let's graph one of the planes from a previous problem here. Let me get rid of all this. I could go, okay, what does the plane x minus 2y plus z equals 0 look like? And it'll give me a portion of the plane. So it's kind of purple there. I hope you can see it. And notice it does look like it's intersecting the origin there. Can you tell just by looking at it? It does. So it is intersecting the origin for sure. And if you wanted to do two planes at the same time, certainly, 2x plus 3y minus 2z. There's another equation for a plane. What the hell? And now you've got two planes. Woo! I'm just rotating it around. Look at that, baby. And can you see right where they intersect? You can imagine a line of intersection there. That's an infinity line of intersection between those two planes. Pretty cool, huh? Now, what's kind of cool, if I rewrite this plane in terms of z, which is not my favorite, okay, actually, well, you know what? Let me leave that guy. Hold on, let me just copy him down again. I like that guy. Okay, how about, let's see, this guy is kind of easy to rewrite in terms of z. If I just subtract the x and add 2y to both sides, I'll get the same plane. It's not different. It's like, okay, negative x plus 2y. You get the same plane. It's not different. But what's cool for this particular software, this is just my software, because it's written what's called an explicit form. Stop rotating, you're making me seasick. You can change its color to rainbow. Oops, sorry. Rainbow. Woo, that's really pretty. The other guy, the other equation, because it's written in implicit form, you don't have as many color options. I can change his color, like, oh, I'll go for green. Okay, fine. That kind of blends with the other guy does, so that's not a very good color choice. So how about we'll change the other guy to stripes. Whoa, that looks pretty cool. So you just have different options depending on whether your equation is written explicitly or implicitly. So when we solved it for z, that was writing the equation explicitly. And you better know this vocabulary in about a month, because if you don't, you're going to be totally screwed. So I'm just introducing it kind of early. Okay? Kind of pretty. Kind of fun. Let's move on. All right, now you're going to sketch a plane in space. Oh yeah, baby. Well, and this is without a 3D grapher. I want you to do it by hand. So it's pretty easy based on some of the things I just told you. So the trick is going to be, oh, by the way, this is a vocabulary word. That line of intersection is, stop, I don't want that. It's called a trace. Excuse me, not the line of intersection, but when a plane intersects the coordinate plane. So let's talk about this in a moment. So I'll show you in the next example where the trace is. And I know I'm talking at you a lot today, but today is a dazzling lecture where I'm just trying to rip, roar, and snort. It doesn't look like I'm going to finish much. So I'm going to do, for sure, I'm going to get through sketching, and then I want to do the distance formulas, and then we'll call it. So when you sketch a plane in space, you find the points of intersection. So there's two things you need to do. Find the points of intersection with the axes, if there are any, because sometimes there aren't a whole bunch, and then draw the traces in the coordinate planes. And if you have no idea what I'm saying, of course you don't, because you haven't seen the action. I'm just giving you the strategy, and then we'll follow the strategy. So check out letter A. Look at letter A here. You're going to draw this in 3D. Keep in mind the x-axis has to go to the left, the y-axis to the right, and the z-axis has to go straight up. Our physics brethren do it a little bit differently. They have a different orientation, and if I see you drawing on your paper the physics orientation, I'm going to mark you wrong. Do it the way the book does it, the way we do it in class. So how do you get the x-intercept? Well, you force the y and z coordinates to be 0 just by substituting in the equation, and then your equation looks like 3x equals 12, and then you get x equals 4. So what are we saying? The point 4, 0, 0 right there on the x-axis is going to be a point in the plane. How do you get a y-intercept? Well, you physically force the x and z coordinates to be 0. So in your equation, you'll have 2y equals 12 or y equals 6. So here at the 6, this point 0, 6, 0 lives on the plane. And then finally, for your z-intercept, you're going to set x and y, force it to equal 0 in your plane equation over here. And you'll have 4z equals 12, but that means z equals 3. So the point 0, 0, 3 is a point on your plane. And now you draw traces. This line that connects the point 0, 0, 3 with the point 4, 0, 0 is the trace as the plane cuts through that xz plane. That's known as a trace. The trace as it cuts through the yz plane is that line, and the trace as the plane cuts through or pierces the xy plane is that trace right here. These are the three traces. And you're done. You have just drawn a portion of the plane. And I hope you can visualize that this is just a triangular portion of a plane that actually goes off in all infinity directions. But at least you get a feel for where it resides in the system. And we're done with letter A. Letter B, keep going. How do you get an x-intercept? Well, you force the y and z to equal 0. But there is no y. I know. But it's still a legitimate plane equation, because the x and z powers are raised to the power of 1. So that's an equation of a plane. So if you set z equal to 0 and then solve for x, you get x equal to 1/2. So on the x-axis, at the point 1/2, 0, 0, that is going to be a point on your plane. And then the z-intercept, similar, set x equal to 0, and you'll just get z equals 1. Okay, so this point, 0, 0, 1, lives on the plane. Now you're only going to have one trace here. And the last problem was a little easier. You had 3 traces. We only have 1 trace. And then a lot of students draw that on their paper, and I go, no, that's a line. Thanks for sharing. Congratulations. You just drew a picture of a line. I need a plane. This is hard. Watch closely, people. You're going to extend that line in the positive y direction to help you see that this is really a plane that's parallel to the y-axis. In other words, it never touches the y-axis. But it's still a plane. It's legit. Last but not least, another type of equation of a plane where you have 2 variables that are missing, not just 1. Uh-oh, now what? Well, what y equals 3 means is that there are no x or z intercepts. So you don't even have to worry about those puppies. What does that mean? This is going to be a plane parallel to the xz plane. Well, how do we draw it? Well, we do know that the point 0, 0, or excuse me, 0, 3, 0, which is here on the y-axis, is definitely going to be a point on the plane. Okay, fine, but is that it? Are we done drawing the plane? Hell no. Come on, that's just a point. That's not a plane. Don't try to joke around with me here, and I'm not going to give you credit. You got to draw an actual plane here. So I'm going to try as best I can, I'm not that good in 3D, to draw a plane that's intersecting the y-axis there at the 3, but a plane that's also parallel to this xz plane, and I'm done. Now let's do distances. Distance between a point and a plane, not too hard to do. Distance between a point and a line, a little bit trickier. So we're going to do both distance formulas. If you're a 3D type of person, especially if you're computer science and you're into gaming, you want to be able to think in 3D like we're doing and draw stuff in 3D and visualize in 3D. It's really important. If you're going to do graphical rendering, you got to think in 3D. And so distances are pretty important, because if you're in a, doing some code for a game and you want to figure out the distance between the enemy and you, And that might depend on if you're a good shot with whatever, if you're trying to kill off all your enemies in the game. These distance formulas might be really helpful. Okay, first up, the easy one. Suppose somebody gives you a point that's not on the plane, right there, Q. And you do have a plane, and you want to find what's the shortest distance between that point Q and the plane. And anytime I say the word distance, it's understood to be shortest. Last semester I had a student, oh dear God, God bless him. But on a quiz, he gave me some weird answer for the distance between a point and something else. And I went, no. And he goes, well, it is a distance. And I went, you didn't say the shortest distance. And I went, dude, it's understood to be the shortest distance because there's infinity answers. Do you see I could draw all kinds of different line segments from my point Q to my point P? I don't care about any of those distances. Shoot, the longest distance would be infinity. I want, when I drop a perpendicular down to the plane, I want the shortest distance. It's obvious. So what's the length here? How do you even get it? It turns out, people, that you involve projections. Really? That never goes away. You're going to take a point that lives in the plane, form the vector PQ here, and then you're going to project it onto the normal vector n. What do you mean? And because when you project it over here onto the normal vector n, you get that vector which has the same length as d. So the magnitude of the projection of PQ onto n is essentially our distance. That's what we want. But you're not actually going to have to do projections because I'm going to do all the hard work for you. So I'm going to do in slow motion and then we'll get to the actual answer. So don't actually do that. You know from projections that the projection of PQ onto n is going to be a scalar times a vector. It's going to be a scalar times the vector n. So the scalar is going to be the dot product of PQ with n all over the magnitude of n squared. But then when you take magnitude of a magnitude, that doesn't really do anything. It's like, this denominator stays the same. But you are going to take the magnitude of n there, and then you can't take a magnitude of a dot product. It just turns the dot product into some positive scalar, so you put absolute value bars around it. And then after reducing this formula to lowest terms, you get the actual formula that I want you to use for the rest of the semester. And here it is. Your distance between a point and a plane is a dot product, absolute value, because you want it to be a positive number, divided by the magnitude of your normal vector. Now, the hardest part when I see students do one of these kinds of problems is cherry picking a point P that lives on your plane. And some students choke and they just use, like, I don't know, any number they feel like is pretty. It's like, no. You need a point that actually lives on the plane. And I just showed you when we were sketching planes how to easily get points that live on planes. The quickest and dirtiest way is to grab an intersection of that plane with one of the coordinate axes. That's my personal favorite way to grab a legitimate point that lives on your plane. Don't blow this, people, because the rest of the problem will go down the toilet. So D is, in fact, this. And that's what you're going to use. But get that point P on the plane. And that's kind of the hard part. So let's go do a problem. Example 7. Here's a point that's not on the plane. You want to find that distance between him and your plane, the shortest distance. Well, how do you do it? Well, get a point P over here that lives on your plane. Well, I don't know. Here's my plane. How about we get the x-intercept? That's pretty easy to get. That's where you force the y and z to be equal to 0, and then you'll have 3x equals 6. So the point 2, 0, 0 is going to be a point on your plane. Oh, sorry. And then your point Q, not on the plane, is given. The only ingredient now is what is the normal vector to the plane? Quick. Like, what is that vector n? You can cherry pick it. How? Okay. Isaiah, are you there?
Yeah.
Okay, cool. What are the components of the normal vector to this lovely plane? Go.
3, -1, 2.
Fantastic. Thank you very much. Does everybody agree with Isaiah?
Yes.
Okay, so now you have all the ingredients. So next you're going to form the vector PQ. So PQ, if you use terminal minus initial and all that good stuff, you're going to get 1 minus 2, 5 minus 0, negative 4 minus 0, and you'll get this vector, negative 1, 5, negative 4. Beautiful. You got your n, so using this formula, I'm just going to write it down again to remind you, this is the formula, and we have all the ingredients. You're going to take the absolute value of negative 1 times 3 plus 5 times negative 1. I'm doing the dot product here, plus negative 4 times 2. Make sure absolute value. Got to have a positive number here. All over the square root of 3 squared plus 1 squared plus 2 squared. So I get absolute value of negative 16. All over square root of 9 plus 1 plus 4, which I believe is 14. And then that is positive 16 over square root of 14. There's the exact answer. If they ask you for the approximate answer, that means go whip out the calculator, and it's approximately 4.28 units. And that's the short distance between the point and the plane. Okay, I'll pause for questions.
So real
So,
quick, no,
okay.
go ahead, David.
All right, sure. Quiz due Monday, no class Monday, right?
Yep.
All right.
To get
Yeah.
the components of n, just look at the coefficients of the plane given.
You got it.
Okay.
That easy. But that seems too easy. Okay, sometimes you got to accept a gift when you're given one. I'm not going to do example 8. I don't have time, but I'll set it up. I want to get to the point and line distance because that's the hard one. What if you have two planes? They could be parallel, or as you saw before, they could intersect, right? That's the two possibilities. How would you prove quickly that these two planes are in fact parallel? I claim they are, but why is it obvious? Why is Captain Obvious going to help you out? I'll give you a hint.
They're multiples of each other?
What's multiples of each other?
The normal vectors?
Very good. So you're going to prove that n1 is a multiple of the other normal vector, okay? And I hope that you can see that if you cherry pick the normal vector from the first plane, you get that vector. And when you cherry pick the coefficients of the variables on the second. So if you, I hope you can see those are, in fact, multiples of each other. Now, how do you find the shortest distance between these two planes? So there's D. So the way you're going to do it, I'll step through. Find a point P on the first plane. And you can do that by finding an x-intercept, a y-intercept, or a z-intercept. I'll just let you do it. Step 2, find a point Q, and this is a point, not vectors, points. There is a difference. On the second plane. So you're going to find some point here and some other funky point here. That's going to be steps 1 and 2. Do it in that order. Step 3 is go find this vector PQ. You know how to find a vector given 2 points. And then you can use the distance formula where you take PQ dot product with either N1 or N2. It doesn't matter, but you got to pick one. And once you pick one, you have to stay in that lane. You'll still get the same answer if you use N2. I don't care. You'll still get the same answer. Okay, and I'm giving you the answer right there. Go do it. Now let's do the hard one. How do you get a distance between a point that's not on your line and the line? And it's the shortest distance. Okay, please don't do what that student did last semester and go, oh, well, I didn't know you meant the shortest distance. Okay, don't even go there. Like I just zeroed out that problem on the guy's paper. And he had a little bit of a temper. And a lot of times after I graded exams or quizzes, the next class meeting, he would like prove how angry he is by not showing up to class the next class meeting. Doesn't hurt me none. It hurt him a lot because him not showing up to class hurts. Okay, so the answer is going to be, oh, here's a picture. Here's Q, here's a point, here's a line, here's a point P on the line. You're going to form a vector PQ, and then the distance, if I drop a perpendicular, this distance here, D, is going to be found by taking the cross product PQ with a vector. I'm just going to call the vector U for now, and then divide by the magnitude of U, where U is just a direction vector for the line. So this one's harder because you have to get a cross product, and that's always a pain. And then you have to take a magnitude of a cross product. So it takes a lot longer to find the distance between a point and a line than it does a point in a plane. Oh, by the way, the man too angry to attend class, men are not the only one that are guilty of that particular sport. I have women do the same thing. I didn't get my grade I wanted. Okay, screw her. I'm not going to come to class. Fine, you're only hurting your own education. You know, if you want to sit there and sulk, that's up to you. But it's you know, what I do, you know, I give you full carte blanche to cry all you want. I cry all the time, okay? Especially now that we're teaching remote. You know, if you want to get in, you know, in the pity pot, grab a number. There's a long line. So here's a picture. Here's your line L. How come the cross product gets involved? Here's your point Q. Here's your point P. We want this distance here, the shortest distance between. How do we get it? Well, after you form this point PQ, you'll know, and let's say your U, that's just a direction vector on the line. I'll just put it right there. See how there's an angle between the direction vector and the PQ? So if I use this triangle here, which happens to be a right triangle, and use my SOHCAHTOA, sine theta is opposite over hypotenuse, I hope you see that the opposite side length is in fact the length of the distance that we want. So we want this. So sine theta is going to be the unknown, D, all over the hypotenuse. But the hypotenuse is the length of the PQ vector, the magnitude of PQ. So if you solve this for D, you'll get D is equal to sine theta times the magnitude of PQ. Fine, but you're not going to use that formula. You're going to multiply that by a special version of 1. And this is the trick in the proof. I know you're going to go, really? And I'm going to go, yeah. The special version of 1 is going to be the magnitude of this direction vector U over the magnitude of direction vector U. Really? And then from a previous theorem, the sine theta of the product of the magnitudes is the same as the magnitude of the cross product. And that's the end of the proof. Okay, so let's now, in the last 5 minutes of class, find the distance between a point and a line. And we'll round the answer. And I give you the answer there. But before I do, one of my colleagues who sometimes teaches this class, when we were discussing this student from last semester who got all pissy because when I asked for the distance between a point and a line, he gave me, you know, this distance here. Like, oh, that's a distance. Yeah, it is, but it's not the shortest distance. Okay, so we were trying to think of analogies to like, well, how does that relate to the real world? So if you had a boat here, and I know this is not a very nice picture of a boat. There's a boat, and then here's the coastline. And then somebody in the boat wants to know the distance between the boat and the coastline. Wouldn't that person, Captain Obvious, give the shortest distance between the boat and the coastline? That person wouldn't go, ahoy, there's land. Oh, by the way, we're 57,000 million miles away from land by, you know, taking this distance here. That would be ridiculous, okay? So just think about that when you're being asked to find distances, okay? It's understood to be shortest distance. Okay, so back to the problem at hand. What is an obvious point P who lives on the line? I'll give you a hint. You're going to cherry pick from the parametric equations of the line, but be careful what you cherry pick to get a point on the line, not the vector. It has to be a point, so I got to use parentheses. Anybody have any idea what those coordinates of the point will be. Go.
Can you set t equal to 0?
You could, that would do it, and then it would give you what points?
The -2, 0, and 1.
Very good. There's a point on the line. Fantastic. So there's our point P. Now what? Well, they gave you the point Q that isn't on the line, that you're trying to find the shortest distance. So you're going to form the vector PQ, because that's going to be needed in your formula. Fine. So this is easy, because PQ is going to be, let's see, what, 3 minus -2, -1 minus 0, 4 minus 1. Great. His components are 5, -1, 3. Fine. Now what? You're going to take a cross product of PQ and U, but what is U? Let's get that first. So get U, who is the direction vector for the line. Do some cherry picking now, quick.
Is it
It's going to be
3, -2, 4?
Fantastic. Congratulations. You just got the direction vector for the line. Beautiful. Now, go get the cross product. And I'm going to use the I hat, J hat, K hat. I've got 5, -1, 3 here, and 3, -2, 4. And then you know you're going to do that whole business of the 3 by 3 determinant. I'm running short on time, so I'll just say you do it. And by the way, on your uploaded work, don't go, hey, teach, you do it. Nice try. I expect you to do, I want to see the full process. Okay, if I don't see the full process and magically the cross product occurs, and I don't want to hear, well, that's how you did it in lecture, teach. I'm doing that because I'm just short on time. All right, you do the whole kit and caboodle. All right, so 2, -11, and -7 happens to be the cross product. Okay, now you're ready, because D is the magnitude of this cross product divided by the magnitude of our direction vector for the line. Fantastic, we're almost done. So you're going to go square root of 2 squared plus 11 squared plus 7 squared, and that's going to go all over the square root of 3 squared plus 2 squared plus 4 squared. Okay, so how are we doing here? Emily, did you get all that? Yay! I'm turning the entire class into fruit pickers. That's right. You don't have degrees yet, so there you go. So then what? Well, then you do the arithmetic, and this turns out to be, square root of 174 over square root of 29. Now, you wouldn't think this happens, because this rarely happens, but let me just finish this problem out. It turns out that a quotient of radicals is the same as a radical of a quotient, and it turns out that 29 divides 174 evenly. Really? I know that's not obvious. It turns out it's just 6. And that is the exact answer, and the approximate answer is 2.45 units. Okay, I'm done. I want to say the rest of the lecture I don't have time for, but you're still responsible for it. That's correct. Well, you didn't do it in class. Too bad. Here's the tip. Go into your modules, and that full completed lecture is here for you, okay? So look at all these extra problems I did by hand for you. Well, that's my terrible handwriting. But hopefully that will help you finish out the rest of the lecture, because those problems are similar to homeworks and quizzes. Okay, see you later. Have a good weekend. Labor Day holiday. We'll see you back here Wednesday. Don't forget, quiz 2 is due. It's opened up on Sunday morning, and it's due on Monday morning, uploaded and everything. I'll stay for 5 minutes, and then I have to go to my next class. So otherwise,
So when you said that we're responsible for the portion you didn't cover, do you mean that that portion you didn't cover is going to be on the quiz?
yes.
Oh, okay.
Yeah, you go. I don't have time to do everything in this lecture. And a lot of those are double whammies, and they're kind of hard. So read the thing, go study. You know, if I were you, I'd study right away.
Yeah. I'll
Do
get
your
to studying
homeworks.
then.
Do your homeworks and look at the view and example button if you need to, if you're not getting it. But if you understand parametric equations for lines and how to cherry pick a point off a line and the direction vector from a line, and you understand how to get equations for planes, and you know how to get the normal vector to a plane, and then you understand about cross product and so on, because you need that, then those extra problems, you'll understand them.
Yeah, I found today's lecture to be surprisingly concrete and non-abstract, so it just takes practice now.
Well, God bless you for that appreciation and validation, George, because I rarely get it. I don't even try to look for it anymore, but I'm just going to say you made my day.
All right.
Thank you so much. It's a pleasure. All right, David, you want to check some freaking code right now? Are you serious? No, not right now. I'll proof check it at the office hour, okay? Everybody, not even coffee can carry my attention for the last 15 minutes. Sorry about that, Vanessa. I don't know what to say. I hear you. I feel your pain, though. It's hard learning online. Okay, so anybody else still in the room? 12, 11, we're losing people. Anybody have their hair on fire and want to ask me a last minute question? Bye, Pete.
I just wanted to ask what pages you said that we're responsible for, the rest of
The rest of this
13.5?
lecture.
Okay, cool.
Yeah, which is
Just
posted.
double checking.
It's posted for you.
Okay.
Yeah, and you're going to see, you know, if you go, I don't understand your posted notes, you know, even though you gave us detailed solutions. I'm like, okay, go do the
It'll be
homework,
fine.
because
Yeah.
you'll just hit the show an example button and hopefully it'll be clear. I don't know.
Yeah.
Maybe.
No, it'll be fine.
Okay.
I'm
Good
just
luck.
double checking.
Good
Thanks.
luck.
Bye.
Okay. Anybody else? We got 3, 2. Somebody in the room? And we're done. Bye.